Hey guys, in this video we're going to look at compound probabilities. So that would be things that use the words like and or. So we're just getting a little bit further into what we started with our tree diagrams, things like that. So a compound probability, like we said, uses words and or. And it says you can solve them without constructing a sample space. You could fall back and do a sample space, but sometimes it's just way too much and you don't want to. So when it talks about or, you're going to be adding probabilities, because it's like two things you could get, so you would add them together. So the or, you would add the two probabilities, and the important part here is that you subtract the overlap, because that means you would have counted that twice. You would have counted it here and here, so you have to subtract it one time so that it doesn't mess up your count, basically. And down here we talk about mutually exclusive. And that's if they are impossible to happen at the same time. So if they cannot happen at the same time, we don't need to worry about subtracting it. But it would just be a zero. If you didn't think about this as a different formula, just think about it as the same, but now this becomes zero, so you're subtracting zero, and it just doesn't matter. But we can use that formula in reverse to make sure that, or to find out if events are exclusive, mutually exclusive. All right, using a standard deck of cards, what's the probability of drawing a king or a red card? So, probability of king or red is the probability of getting a king plus the probability of getting red minus the probability of getting a king and red. So they're like a red king. Put that together as just one thing. So probability of being a king, there's 4 out of 52 cards that are kings. Probability of being red, that's half of it. There's hearts and diamonds are red, clubs and spades are black, so that's half. But then we subtract probability of being a red king. There are 2 red kings in the deck out of 52. These could have all been reduced. I obviously reduced the red, but because that would have been 26 out of 52. But we can reduce them all and then add and subtract. Or if we wouldn't have reduced, we would have had common denominators off the bat, and that would have been pretty easy. What did I say, 26 over 52? So 4 plus 26 is 30. Oops. And then 30 minus 2 is 28. And then you can reduce that. Divide by 2, we get 14 over 26. Divide by 2 again, we get 7 out of 13, and that does not reduce any further. And you could have done this with a calculator. You wouldn't even have to reduce in that case. They don't need to be common denominators on the calculator. It can take care of that. So that's 4 out of 52 plus 1/2 could be 0.5. It's easier, I think, to type. Minus 2 over 52, and it'll do all of that for you. Gives you a decimal, but if you hit fraction of decimal, it'll convert it, and it's the same answer. So, calculator or do it by hand, doesn't really matter. All right, using a standard deck of playing cards, what's the probability of drawing a queen or a club? So probability of queen or club. That is the probability of a queen plus the probability of a club minus the probability of a queen that is also a club, and All right, so queens, that's 4 out of the whole deck. 52. Club, that's 1 of the 4 suits, or you could say 13 out of 52 if you want to keep the denominators the same. It makes it kind of easy. And then queens that are also clubs, that's just 1 card out of the entire deck. But you see, we counted that card twice. We counted it as a queen and a club. That's why we have to subtract it 1 time. All right, so that's 4 plus 13 is 17. Minus 1 is 16. And then that can obviously reduce. Divide by 2. Divide by 2 again. And that's it. And then you can also write these as decimals if you wanted to. It doesn't really matter. All right, each of the numbers 1 through, make sure we're not skipping anything, being tricky, 10 is written on a separate piece of paper. The 10 pieces of paper are placed in a hat. 1 piece is randomly selected. Determine the probability that piece of paper selected contains an even number or a number greater than 6. So probability of even or greater than 6. Does not say or equal to 6, so it's just greater than 6. So we got probability of even plus probability of greater than 6 minus probability of even and greater than 6. So the even numbers from here would be 2, 4, 6, 8, 10. That's 5 of them out of 10. Plus greater than 6, that would only include 7, 8, 9, and 10. Minus the probability that it even and greater than 6, so that would include 8 and 10. It's 2 out of 10. So these obviously have common denominators already. That's 9 minus 2 is 7. And that doesn't reduce. Six-sided die is rolled. What's the probability of rolling a 3 or even? So that's probability of a 3 plus probability of an even minus probability of being a 3 and even. Whoops. All right, well, 3 is not an even number, so that's 0. So that these are mutually exclusive because those cannot happen together. Probability of a 3, that's 1 out of 6. Probability of an even, that could be a 2, 4, or 6, which is 3 options. So that's 4/6, which is 2/3. It's your probability, 2 out of 3. All right, we're looking at probability of being a black or heart. Draw a symbol this time. All right, probability black plus probability of a heart minus the probability of the card being black and a heart. Well, the hearts are red, so they're not black, so that's 0. They're exclusive. Hearts are 1 out of 4. Black is 2 out of 4, or 1/2. I'll do 2 out of 4 so we have a common denominator. Add those up, that's 3/4. Or you could have done 26 out of 52, 13 out of 52, added them up, it would have reduced the same way. All right, so and, when we're talking about and, you actually multiply those probabilities together. So or means add, and means multiply for probability. So the probability of 2 things happening, you would multiply the probability of those together. And then you always have to assume that the first thing happened when you're calculating the probability of B. So that mainly just matters for times when you do not have replacement, when you don't put the numbers back in there, or whatever it is, when you don't have that option again. So independent events, the occurrence of any two or more events in no way affect the probability of the others. They don't have any impact. They're independent. Dependent means that it does have an impact on the other. So experiments done without replacement are always going to be dependent. Because the first thing, you take it out, you don't put it back, which is going to change what happens the second time. So what is the probability of drawing two aces in a row with and without? So probability of drawing two aces in a row, so that's the probability of drawing an ace and another ace happening two times in a row. So the probability with replacement. So the first thing does not impact the second thing. We're going to multiply them. Probability of getting an ace is, that's one of the 13 cards, so that's 1/13th. And another ace after we put it back there, so it's still going to be 1/13th. So two aces in a row is 1 out of 13 times 13 is 169. That's pretty small. That's less than 1%. Without replacement means first to draw an ace, that's 1 out of 13, but the second time it's not going to be 1 out of 13 again, because now there's only 3 aces left, and there's only 51 cards because we took out one card because we took out an ace. So when we are multiplying, we multiply the numerators. Let's get that over so we can see. 1 times 3 is 3. And we multiply our denominators. 13 times 51, 663. I think that's actually going to reduce. One out of 221. So you can see a little bit less likely. If you put those as decimals, sometimes it's easier to see if you just say like 1 plus. So you can actually see the decimals there. And then 1 out of 169 from that first part. Compare the decimals if you wanted to. So this would be a 0.0045, and this would be 0.0059. So you can compare them that way too. That's like 0.45%, and this would be 0.59%. Really, really low chances, really. Bag of marbles contains 5 red, 8 blue, 5 yellow, 6 green. Select 3 marbles without replacement. Find the probability that the first one is green, the second one is red, and the third one is blue. So the probability that we go green, and then red, and then blue. So probability of going green first is 6 out of, let's add these up. That's 10, 18, 24. All right, and then the next time we're going red, we take out a green one. So that means we have 5 reds left. But we no longer have 24 marbles, we have 23 in there now because we took out a green one. And now our next would be a blue. So we've taken out a green and a red, so there's still 8 blue, because we did not take out a blue. But now we've taken out 2 marbles, so instead of 24 or 23, there's now 22 marbles. So we can multiply our numerators. It's 240. We can multiply our denominators. One, 2, 144. And we can type this in, we can reduce it. If you just type it as a fraction, I think your calculator will automatically reduce. You don't even have to do the 2 steps there. There it goes, automatically reduced to 5 over 253. If we hit fraction to decimal, there we go. It even gives us the decimal if you want. That's almost 2%, if you want to think about it as a percentage. It's close to 2%. Two cards are dealt successively. It actually doesn't matter if you're dealt successively or not. The probabilities will be the same. But from a standard deck with replacement of the first. So you do put the first one back. Find the probability of getting a red card and then a heart. So first, I'll just do H for heart this time, because last time I drew a heart it wasn't very good. Probability of getting a red card, well, that's half of the cards, and then you put it back. So that makes our next calculation easier. A heart is 1 out of the 4 suits. So on multiplication, that's 1 times 1, 2 times 4. There you go, 1 out of 8. Which is 0.125 if you wanted a decimal, or 12.5%. All right, 3 cards are dealt without replacement of the first or the second. You don't put either one back. Find the probability of getting. So this last one was replacement. Now this one is not replacement. So this would be more like an actual card game where you deal 3 cards to somebody. But we're not putting them back because they're going to hold on to those. So then find the probability of getting a club, a spade, and then a red card. So we're going probability club, and then spade, and then red. So this is without replacement. So clubs, that's 13 out of 52. And then spades, there's 13 spades also, but now we're missing 1 club from the deck, so now there's only going to be 51 cards to choose from. And now we've taken 2 cards out of the deck, so there's 50. And we're looking for a red card. So red was half of the original cards, which is 26. We took out a club and a spade, which are both black. So there's still 26 red cards. So we have 13 times 13 times 26, 4394. And then our denominator, 52 times 51 times 50. $13.26.00. All right, so we do want to reduce that, so now we'll type it in. You could type this whole thing in as a fraction, but I like to see it in steps. Whoops. 1, 3, 2, 6, 0, 0. And this will definitely reduce a little bit. Let's see. 169 over 5100. And if you wanted a decimal, just push the F to D button. So a little bit over 3%, 3.3%. All right, 6 cans of soda in a cooler, 3 colas, 2 diets, 1 caffeine free. If you choose 2 without replacement at random, what's the probability that you will open at least 1 cola? So when it says at least 1 cola, either one could be a cola. The easiest way to go about these, and I think we talked about this in a previous lesson, at least 1 would be to figure out what it would be to not get a cola and do 1 minus the probability of getting no cola at all. That would mean that you get at least 1. Because it's okay to get 1 cola or 2 colas. There's a lot of ors involved there, and the easiest way, I think, is to just do the probability of getting no cola. So that means the probability that you reach in and you grab a first can that is not a cola, and then you reach in and grab another can that's not a cola. So we're looking at probability of no cola and no cola. So the probability of going no cola on the first one, and again, this is without replacement. So there's 3 colas in there and 6 cans total. So that means 3 of them are not cola, 3 out of 6. And then the second time, still no cola. Well, we just took out a can that was not a cola. So now there's not 3 cans that are not cola. There's 2 cans that are not cola. And there's not 6 cans anymore because we took 1 out. So there's only 5 cans left. So that's 6 out of 30, which is 1 out of 5. So that's the probability of getting no cola, which means the probability of getting at least 1 cola would be 1 minus 1/5. Or you could rewrite that as 5/5 minus 1/5. Common denominator, which means you have a 4 out of 5 probability of getting at least 1 cola. Alright, that's it. Get your homework done, find it in the Files tab, post your comments and questions, and see you in the next video. Bye.